Yeah, welcome back again, physical sciences learners and teachers, fanatics of the subject. This is another Doppler effect. So problem solving. Remember the phenomenon Doppler effect. We say it happens only if there's a relative motion between the sound source and the listener. Fine. Now this is a question which is recent, non-retrial papers. A siren of a stationary train emits sound waves of a constant frequency of this one. So this is emitted by the siren, therefore is the frequency of the source. A person in a car with a detector accelerates constantly from rest. You underline the word from rest, therefore initial velocity is 0 there. At point X towards the train, so the movement is towards. Fine. Take the speed of sound in air as 340. This is V. Now they say to us, name the phenomenon that was observed by the listener. So this one, without a doubt, is the easiest. It will be the Doppler effect. Doppler effect. So free mark there. Calculate the wavelength of the omitted sound waves. Remember, there's only one formula with wavelength. That is your V equals to F multiplied by lambda. This is the speed of sound, which is 340 according to the question. Frequency is given is 780 from the statement. If you look at the statement on top there, fine. And we are determining the wavelength, the lambda. Therefore, lambda will be the same as 0.44 meters. If you use your calculator, you get 2 marks for doing that. 6.3. Now they say to us, explain why the observed frequency is higher than the emitted frequency. In this case, why is it higher? We said once there are three things: motion, frequency, and wavelength. Now the motion is towards is given, so why the frequency is higher, then it will be the wavelength is decreased. Wavelength, that's the first point. Wavelength decreases when the motion is towards. And the second point now will be about when the motion is towards, then what happens to the number of waves per second. Because the frequency is higher, they say now more waves are approaching. In this case, more waves reaches the listener per second. That is the frequency. Remember, the frequency is the number of waves passing through a point per second. In this case, 6.4. They now say, according to statement at Y, is 83.11 meters from X. The person in the car measures the observed frequency as 850. Now we have this as frequency of the listener, is the detector. Therefore, now they say calculate, number one, the speed of the car, the VL. Then we write the Doppler equation. This is 5 marks. So Doppler equation will be used. V plus or minus VL divided by V plus or minus VS multiplied by FS. Therefore, FL is given is 850 according to the statement. V is 340. Because the motion is towards, then we'll start with the plus. The listener is the one I'm calculating. I will just write VL. And then 340 minus 0. Then the source is emitting the frequency of 780. That's the case. Then from here now, you will just work it out and find with your calculator. You will now ending up with 30.51 meters per second. Because remember, why this is 5 marks, the whole formula with substitution below will be 1 mark. 1 mark for substitution of 780, 1 mark for substitution of 850, 1 mark for the whole fraction here, and then 1 mark for the answer. That's how the 5 marks is allocated. 6.4.2, they say to us now, calculate the acceleration. If you look at this, what is given, we said, if you still remember from the statement, the motion starting from rest, delta x is given from the statement. You can see delta x from x to y is 83.11. And then what else do we know? We know the final velocity we just calculated now, 30.51. Then we need acceleration. So you go for the formula without delta t. If you look at this, it will be of vf squared equals to vi squared plus 2a delta x. Vf squared is 30.51 squared equals to 0 squared plus 2a multiplied by 83.11. Then from here you can find the value of a. The value of a, according to the calculation, if you use your calculator properly, you'll find 5.60 meters per second squared. That was the last question here. There's no Doppler of light. There's no uses of Doppler, which is not a train smash, but that's one of the good questions that was asked to learners in the past years, and then these were the answers. I think it makes it easier and reasonable to say Doppler is the easiest one to deal with. So hopefully you will be also able to entertain it. If you can quickly go through one last question. Here is the one. It's question number 6 again. They say to this one, a car initially at rest has its radio play music. The diagram below, not drawn to scale, represent the sound waves wavefronts arising from a musical note of a frequency of 440. Therefore this one is fs. Fine. Spreading out from the car, the speed of sound in air is 330. That's your v. Then calculate the wavelength of the sound wave. We said there's only one formula with wavelength. Then it will be v equals to f multiplied by lambda. 330 equals to frequency is given, it's 440. Then multiplied by lambda. Then you get out of this one, lambda will give you somewhere around 0.41 meters. Fine, no problem. Then you get to 6.2. Fine. Now they're telling us what is the frequency of the node as heard by the observer at point A, because both the source and the observer are stationary. Therefore it means that the emitted frequency and the detected frequency will be the same. Therefore it's 440 hertz. 6.3, 440 hertz. 6.3, they say, what is the frequency? Oh, sorry. The car now moves at a constant speed. That's your VL. The car is the one that is having the source. Therefore, it's VS, this one. And the wavefronts reach the stationary observer as shown below. Yes, you can see that the motion is towards the observer because the wavelengths are compressed. Write down the Doppler effect in weights. Remember we said Doppler effect is just a change in frequency. As detected of sound. Sorry, change in frequency of sound as detected by the listener due to relative motion between the listener listener, and sound source. That is definition, or due to the listener and sound source moving at different velocities to the medium of sound propagation. That was 6.3. 6.4. At what speed are the wavefronts progressing towards the observer? You see the car is moving, and at 8 meters per second, even the waves will be having the same speed, 8 meters per second. 6.5. Now they're telling us to say, calculate the frequency of the note as heard by the observer at point A. We're calculating FL. Therefore, Doppler equation come into the picture here. Then this will be the case. Copy it the way it is in the examination guideline, in the formula sheet. Please. The listener is the one we're calculating. They say the speed of sound in A is 330 according to this one, and the motion is towards the observer. So we'll start with the plus, and then the listener is stationary, is the sound source that is moving, minus 8, and then multiply by 440. Therefore, if you work out the answer here, it will give you somewhere around 500 something, 530 hertz. So that will be the case, which is your answer in this case. Fine. And that one brought us to the last question of this. So relatively very easy question. It was just talking about the relative motion, the definition, and the interpretations thereof. Hopefully it makes life easier with Doppler. I hope you can understand and you can express yourself if confronted with similar questions. So thanks a lot for now, until we meet again in the next coming sessions, where we're dealing with the other concept, either Doppler or other paper 1 concept, or paper 2 in this case. That's the easiness about the paper 1. Calculations, very easy calculations, as long as you remember the formulas. I said in Doppler there are only 3, then remember them all the time. Know which one, when to apply each one in what cases. Until we meet again, thanks a lot.